Welcome back to the deep dive. Today, we're taking a really focused look, diving into the CSWIP 3.1 Welding Inspector Exam Prep Series. Now, for those maybe not directly involved, CSWIP stands for Certified Welding Inspector Personnel, that 3.1 certification. It's a pretty big deal for welding pros.
It really is.
Think of this as, well, your shortcut to getting the critical stuff down. Not just for the tests, but for doing the job right out in the field. Our mission today is to pull out the key bits of knowledge from some core questions, the ones that really check if you understand the fundamentals.
Exactly. And it's not just about knowing the right answer, is it? It's the why. Understanding the reason behind it, that's what turns facts into, usable knowledge. Super important for grasping these essential welding inspection principles quickly but properly. It's about building that solid base.
Couldn't agree more. So let's jump in. We've picked out 5 questions that really test that deeper understanding. First up, let's talk about welding gear for tricky situations. All right, question 1. Which from the following equipment would you choose for safe, open-site manual metal welding? A, single operator transformer. B, multi-operator transformers. C, AC/DC composite power unit. Or D, diesel engine-driven motor generator.
Right. The answer you're looking for there is D, diesel engine-driven motor generator.
Okay, diesel generator. Let's unpack that. Why is that the go-to for an open site?
Well, that phrase open site is the real key. Think about it. Construction sites, pipelines out in the fields, maybe emergency repairs.
Right.
You often just don't have reliable grid power.
Right. No handy plug sockets nearby.
Exactly. Transformers, those composite units. They're great in a workshop, sure, where you've got mains power. But they need plugging in. And a diesel generator, though, it makes its own power. It's self-contained.
Independence.
Totally. It gives you portability, reliability, everything you need when you're working somewhere remote or where the power situation is, let's say, uncertain.
Okay, that makes sense for getting power at all. But the question mentions safe welding. So thinking practically, what's the danger if someone tried to rig up, say, a transformer with a really long extension cord on site instead?
Oh, that's a classic scenario. And yeah, definitely risky. The biggest issue right away is voltage drop. Long cords, especially if they aren't heavy-duty enough for the current, the voltage just plummets by the time it reaches the welder.
Which means?
An unstable arc makes it incredibly hard to get a decent weld. Plus, it's frustrating for the welder. The electrode can stick. It's just not consistent or safe. And then you've got the physical hazards.
Like tripping over the thing?
Yeah, trip hazards, the cord getting damaged by equipment, getting wet, serious risk of electric shock. A generator gives you stable, isolated power right where you need it. Much, much safer. As an inspector, you're looking at that whole setup, not just the finished bead.
Got it. Safety and practicality rolled into one.
Okay, from the power source to checking the weld itself, especially for hidden flaws. Question 2.
Which bend test specimens that have been taken from a 25 millimeter thick carbon steel butt weld would be prone to show lack of interrun fusion? A, side bend. B, root bend. C, face bend. D, guided bend.
And the answer here is a side bend.
Side bend. Why specifically the side bend for lack of interrun fusion in, well, fairly thick plate, like 25 millimeter?
Okay, so first, what's the lack of interrun fusion? It's basically where 2 adjacent weld runs, or a run and the base metal, haven't properly melted and fused together. It's a gap, essentially, inside the weld.
Like a hidden layer that didn't stick.
Pretty much. Now, in a thick weld, like 25 millimeter, you've definitely got multiple passes, one layered on top of another. A side bend specimen is cut through the weld thickness, so when you bend it, you're putting stress right across all those layers.
I think I see where this is going.
Yeah. If there's a lack of fusion running along the length of the weld, sort of parallel to the surface but buried inside, the side bend test forces that area open. It exposes those internal flaws beautifully. Root bends and face bends test the outer surfaces more, the root and the face, obviously. The side bend is specifically designed to reveal flaws within the bulk of the weld thickness.
That makes sense. Now, you mentioned it's a hidden defect. In the real world, wouldn't you more likely use something like ultrasonic testing, NDT, to find that before you cut a piece out? Or are bend tests still the main thing for qualifications?
That's a really good point. Yes, absolutely. Ultrasonic testing, or UT, is a major non-destructive technique used all the time in production to find internal flaws like lack of fusion without damaging the part. It's essential for quality control on finished welds.
Okay.
But bend tests, especially side bends for thick materials, play a different vital role. They're destructive tests used primarily for qualifying welders and welding procedures.
Proving capability.
Exactly. You're proving that a specific welder using a specific procedure, can produce a weld that's internally sound and has the right mechanical properties. The side bend test, by physically pulling those layers apart, gives you that tangible proof for qualification purposes.
Yeah.
So UT for checking production, bend tests for proving the process and the person, both crucial.
Right. Different tools for different but related jobs. Okay, moving on. Question 3 takes us into the actual welding process, specifically the flame.
Oxy-Acetylene.
Question 3. What would be the effect of using an oxy-acetylene flame with a long feathered inner cone on carbon steel? A. The weld would be hard and brittle. B. The weld could be too soft. C. There will be no effect on the weld. D. The weld will have undercut.
The correct answer is A. The weld would be hard and brittle.
Hard and brittle. Okay, what is it about that long feathered inner cone that causes this?
That description, long feathered inner cone, is the visual signal for what's called a carburizing flame. It means there's too much acetylene gas compared to the oxygen.
Got it. Too rich, like a fuel mixture.
Precisely. And that excess acetylene breaks down in the heat, releasing free carbon atoms directly into the molten weld pool. This extra carbon gets absorbed by the steel.
And carbon makes steel harder, right?
It does, but here it's uncontrolled and excessive. It forms iron carbides, which are very hard but also very brittle compounds, both in the weld metal itself and in the heat-affected zone right next to it. So you end up with a weld that's significantly harder, yes, but it loses its ductility, its ability to stretch or deform, and its toughness, its ability to absorb impacts.
So it sounds like a recipe for disaster in anything that needs to flex or take a knock. What does that mean for, say, a weld on a bridge or maybe a pressure pipe?
It's incredibly dangerous. A hard, brittle weld is like a ticking time bomb in a structure that experiences any kind of dynamic load, vibration, or even temperature changes that cause expansion and contraction. It can fail suddenly, catastrophically, with very little warning because it can't deform to accommodate stress. Yeah. So for Inspector, recognizing that flame characteristic isn't just academic. It's seeing a direct link to potential metallurgical problems that seriously compromise the integrity and safety of the final product. That's why flame control is so critical in procedures.
A tiny adjustment, huge consequences. Okay, let's shift from the process itself to what happens after welding. Question 4.
Right. Post-weld treatment.
Fillet welds need to be blended in by grinding according to a fabricating procedure. This influences A, HAZ, cracking, B, fatigue life, C, residual stress, D, yield strength.
The key influence here is B, fatigue life.
Fatigue life. So grinding the weld isn't just making it look neat.
Not at all, although a neat finish is often a side benefit. The crucial point is the toe of the fillet weld, that transition line where the weld meets the base plate. Geometrically, it's often quite a sharp transition.
Yeah, but the little notch.
Exactly. It acts like a notch, a stress concentrator. When the component is subjected to repeated loading and unloading, that's fatigue loading, stress gets magnified at that sharp toe.
And that's where cracks like to start.
That's precisely where fatigue cracks often initiate. By grinding or blending in that toe, you create a smoother, more gradual transition. You reduce that stress concentration significantly.
So the stress gets spread out more evenly.
Yes.
Wow.
Lowers the peak stress at the toe, which means it takes many, many more load cycles before a crack might start. Or it might prevent it altogether within the designed life of the component. It directly extends the fatigue life.
That's fascinating. A bit of grinding making the difference between something lasting years versus decades under stress. Now, you mentioned other options like HAZ, cracking, and residual stress. How does blending relate to those?
Well, HAZ cracking, heat-affected zone cracking, is more about what happens during cooling, metallurgy, hydrogen, that sort of thing. Grinding after the fact doesn't fundamentally change that risk, though poor grinding could introduce surface issues. Residual stress is the locked-in stress from welding. Grinding can affect surface residual stresses very locally, but the primary intended effect of blending the toe is definitely fatigue life enhancement. And yield strength is just a basic property of the metal itself, not changed by this kind of surface treatment.
Got it. So that blending step in the procedure is really targeting long-term durability. Okay, final question. This one takes us back to the plans, the drawings.
Standards and symbols.
Question 5. What does BS 499 specify regarding the drawing dimension quoted for a fillet weld according to UK practice? A, leg length. B, throat thickness. C, weld width. D, actual throat thickness.
According to BS 499, for UK practice, the answer is A, leg length.
Leg length. Can you just quickly clarify what leg length is on a fillet weld?
Sure. Imagine the cross-section of a fillet weld. usually roughly triangular. The leg length is the distance from the root of the joint out to the toe along each fusion face. For a typical equal leg fillet, it's the size of the two equal sides of that triangle. It defines the overall size of the weld deposited.
Okay, clear. So thinking bigger picture, why is it so important for an inspector, or anyone really, to know that BS 499 uses leg length? Seems like a small detail.
It seems small, but it's fundamental for clear communication. Engineering relies on standards like BS 499 to create a common language. Imagine a designer specifies a 6 mm fillet weld.
Right.
If the fabricator thinks that means throat thickness and the inspector thinks it means leg length, you're going to have problems. The weld built might be significantly different from the weld designed.
Undersized or oversized, potentially.
Exactly.
Yeah.
Which could affect strength, fatigue, life, everything we've been talking about.
Yeah.
Knowing the standard convention in this case, BS 499 defaults to leg length for UK drawings ensures everyone is on the same page. The inspector knows what dimension to check, the fabricator knows what size to make it, and the designer knows their intent is understood. It prevents costly errors and ensures the final product meets the required specifications and safety factors. It's all about precision and avoiding ambiguity.
Absolutely critical for consistency and safety. Okay, that brings us to the end of our deep dive into these 5 key CSWIP 3.1 questions. We've covered everything from generators on site to side bends for fusion defects, the impact of carburizing flames, the importance of blending for fatigue, and finally, how weld sizes are specified on drawings via standards like BS 499. Understanding the why behind these, not just the answer, really does give you, the listener, a solid footing for the exam and, more importantly, for the actual job.
It really does. And maybe a final thought to leave with everyone. Thinking about all this detail raises a broader point, doesn't it? How does truly getting the why behind these technical specifics prepare you not just for a test, but for handling the often complex and sometimes unexpected situations you face, ensuring weld quality and safety out there in the real world?
That's a great question to ponder. It's about moving from theory to practical problem solving and sound judgment. So definitely take these insights, maybe revisit the concepts, and keep digging deeper into welding inspection. The more you understand why things are done a certain way, the better equipped you'll be. Thanks for joining us on the Deep Dive.